Thanks very much. So the discussions that we've had of stratification at the top of the core, we would expect, actually, if this stratification existed, that it would affect the way in which the fluid motion behaved at the top of the core. And so, in principle, we should be able to look for evidence of this stratified layer by inverting magnetic field observations and seeing whether or not the flows that we recover from those inversions are actually compatible with the presence of a stratified layer. Now, we have, or the community at least, has been doing this for quite a long time, but they've often imposed assumptions which are incompatible with that idea. And so the goal here really is to do flow inversions that allow for the kind of flow structures that you expect to get in the presence of a stratified layer, and then ask the question, are those flow structures compatible with the existence of this stratification? And the answer, I'm going to tell you at the end, is yes. So we've heard now a couple of examples of evidence that people have pointed to suggest that there's stratification at the top of the core. The seismological line of evidence, the suggestion that when you look at these multiply reflected waves at the top of the core, there's a suggestion that these waves are slow relative to Prem, and therefore could potentially be representing a distinct layer at the top, which is distinct from a well-mixed layer that Prem is intended to represent. And in fact, the interpretation of this particular observation by George and colleagues is that this really represents a compositional stratification. There's, oops, sorry, wrong. I didn't realize the mouse had two sides. Can I go back? Oh, I see. Okay, good. So mineral physics also provides suggestions that there may be stratification at the top, but this case, thermal stratification. So Monica Pozzo and colleagues a few years ago did first principle calculations that suggested that the thermal conductivities of liquid iron alloys in the core were much higher than we had previously assumed, and we have heard something about that during this session. The basic idea here and the basic issue is that we expect that a core that is well mixed by convection will adopt a nominally an adiabatic profile. But with these higher values of thermal conductivity, the amount of heat that can be conducted down the adiabatic gradient can actually exceed the amount of heat that the mantle will actually remove from the core. So this creates a problem. So that's what's intended to be shown right here. We've got convection in the interior of the core, perhaps powered primarily by compositional buoyancy from intercore growth. We have a well-mixed core and an adiabatic temperature profile, but the heat flow that would be conducted down this hypothetical adiabat, if it were well-mixed, exceeds the amount of heat that the mantle can draw out. And so as a consequence, what we would expect to have happen is that the thermal profile will relax off an adiabat. It will become hotter at the top in much the same way that hot air is accumulating at the top of the room that we're in right now. And the point is that you'll be left with some thermally stratified layer which won't participate in the convection. We'll still have convection down here driving the dynamo, but this layer at the top will be stratified. Okay, so the other line of evidence is in fact the suggestion made earlier this year that there's waves at the top of the core which are compatible with the existence of a particular type of wave that actually depends on stratification for its existence. So it's the ideal diagnostic to go after this particular structure. So the idea was that we have observations or models perhaps of time-dependent zonal flows at the top of the core which are compatible, at least consistent with these things called Mach waves, which I'm going to show you right here. This is sort of an analogous or sort of a representative example of what one of these modes would look like. You imagine that there's a stratified layer at the top here in much the same way that we had this, oops, sorry, going backwards. Maybe we can just, thanks very much. So I'm imagining this is the stratified layer right here, and if you imagine you have small radial motions through that stratified layer, you're going to perturb the density field, you're going to perturb the pressure field in the core, and that's going to drive a nearly geostrophic flow. So the largest component of these waves are actually these geostrophic flow, these zonal motions going around the core. But because we have magnetic fields in the core, there's going to be a small amount of friction, and that friction will induce a secondary flow which will be toward the poles or away from the poles. And so what was done in this study was to try to ask the question, can we explain the time-dependent zonal flows in terms of these sorts of waves and this particular component of the flow? And the answer is that you can. But there's a sort of secondary consequence that once you've explained these zonal flows, there are consequences for these meridional flows, these poleward flows, because they will sweep magnetic field toward the poles. they'll cause the dipole to change, and we would expect to see corresponding fluctuations in the amplitude of the dipole field. And that's exactly what we see. So this is predictions for what we would expect for fluctuations in the dipole field from a period of 1930 to 1990. Using the flow models of Andy Jackson's, which were based on these magnetic field models, GUFM. And the point is, with no adjustable parameters, you just simply fit the waves to the zonal part of the flows and ask the question, what happens? And these two results are remarkably consistent. You can take a more modern flow from, say, 1960 to 2010, and using the same modes that were fit to the zonal flows here, reproduce the same features or the same structures in a more recent flow model that incorporates satellite data. So the point, I guess, is, though, that the direct testing of these flows is not possible because many of the models that actually predict these flows exclude this component of flow, dynamically speaking. And so what we wanted to do was reproduce these flow models and allow for the structure that would be consistent with the existence of these waves. So here's the idea. This is the equation of which all flow models are based on. You're looking at the radial component of the induction field, time variations in the radial field related to the divergence of this quantity. And the point is, you've got one equation. You are trying to extract two components of the velocity field, so it's underdetermined. And so you have to introduce additional conditions, dynamical conditions, that allow you to reduce the non-uniqueness. And so the typical ones that are often assumed is that the flow is either steady, for example, or purely toroidal, which is often been previously assumed to be appropriate for a stratified layer, or it's tangentially geostrophic, where the effects of Coriolis force are dominant in the force balance. And the point is that both of these approximations, which are probably the two most common, permit no poloidal flow. So there's no way to make a direct comparison with what the waves predict and what the flow you recover from these solutions. On the other hand, the Mach wave problem is both time varying and includes both toroidal and poloidal flows. So we want to basically make sure that our inversions account for this possibility. Okay, so here's the strategy, and this is work that was primarily done by Richard Holme, who wasn't able to be here today. But the idea here is that we're going to recover a constant and unconstrained steady flow over the entire period. And then the idea is to remove that component of flow and ask the question, how much variation in the magnetic field is left over after that component has been calculated? And the idea is to extract time-varying flows that account for that residual secular variation. And we'll assume that those flows are zonal, and we'll assume that they're equatorially symmetric, and we'll allow for the possibility that they're purely toroidal, which would be consistent with previous studies, but we'll also consider the possibility that they could have both toroidal and poloidal components. And what's interesting in terms of doing this is what we find is that when you add the poloidal component, the toroidal component doesn't change very much. And so that's good news from the point of view of the previous study, because it means that the toroidal flows, which have been previously estimated, are probably not adversely affected by excluding a poloidal component in the inversions. On the other hand, though, we find that when the poloidal flows are included, there are a lot of good things that start to happen. So, for example, we explain much more of the secular variation, and this is just one example. It's a slightly complicated slide. But what we're looking at here in the black line is the residual secular variation that we're trying to explain. If you allow for just the toroidal part of the flow, you would get this blue line, and you sort of underestimate these high points and much, much smoother. But by allowing for the poloidal flow as well as the toroidal flow here, you're actually able to produce these features which in the geomagnetic community refer to jerks. And so suddenly now features that weren't explainable before, in fact, are possible. So when this is an example of what the flows actually are, right? So this is the steady flow that has been extracted to define a residual, and these are the time-varying flows that are required to fine-tune those variations. And the point is that these flows are relatively small. If these are on the order of, say, tens of kilometers per year, these are sort of at the scale of kilometers per year. Okay. So one of the first things that Richard did when he got these flows was to try to fit the variations in the various spherical harmonic components to wave-like components. And what he found was that you could get a fairly reasonable fit if you assumed a period of about 50 years. And these are the amplitudes and the phases of the different spherical harmonic components of the flow that he recovered in his inversion. So the toroidal part, which is largely a rigid rotation of the core, has the largest amplitude, and then you can see the poloidal and toroidal components going to higher and higher degree. Going to higher complexity, the amplitude goes goes down. And partly that's a regularization in the inversion. What was kind of striking about these results is if you look at the toroidal components, let's say this one here, this is now separated from the next one by 180 degrees, separated by 180 degrees, by 180 degrees. There's a lot of structure there. And you'll also notice in terms of the poloidal motion that the degree above tends to be phase shifted by about 40 or 50 degrees. So these features are actually things that you see in the Mach wave problem, although we don't actually in any individual wave see this exact same pattern. So the better way to test this would be to actually reproduce the exercise that was done previously in that Nature paper. So the idea here, oops, there, you're going to have to let me go back again. Thanks very much. There we go. And one more forward. Maybe you should work this. Okay, so this is the time-dependent zonal flow that was sort of superimposed on the steady flow to explain the residual secular variation. And there's the zonal flows here. This is plotted as a function of the sine of the colatitude, so this would be a flow which is right near the pole, and this is a flow which would be right at the equator. And these are equatorial symmetric, so whatever's happening in the northern hemisphere is happening in the southern hemisphere. And it's a function of time going from roughly 1920 to 1990. And so what's been done here is to fit the lowest frequency Mach waves to this particular flow, and what you're seeing is the result right here. So because this is a relatively restricted, we're just including a few modes, the most low frequency modes. Of course, we're not able to resolve all of the short wavelength structure in these recoveries, but you do see that this feature looks very much like that if you were to filter it to a similar spatial resolution. So here's the point. All that I've done right now is I've fit the zonal part of the Mach waves to the zonal part of the flows. These Mach waves make predictions for what the poloidal flows should do, and we also have direct recoveries of what the poloidal flows should be. So we should be able to compare them and see how well they do. And so this is the result. So this is the degree 2 part of the poloidal flow. The red line is what we get from the waves. The blue line is what we get from the inversion. And then again for degree 4, you see very, very good agreement. But clearly there are some disagreements a little bit, but it's kind of remarkable that there's absolutely no reason why these two things should even be able to be plotted on the same graph. Okay, so the fact that there are small differences, to me, I would call this perfect success. There was something in the morning, I think people were saying, what do you consider success? I would say, even getting these on the same plot is remarkable. The fact that we've got the phase fairly consistent is pretty remarkable to me. So to conclude, I would say that the secular variation at the very least is compatible with a stably stratified layer at the top. We see strong phase coherence between the flow components, which is suggestive of waves, and some aspects of that coherence is actually reproduced in individual waves. But to me, the strongest point of evidence is the fact that we have this relationship between poloidal and toroidal flows, which we can quantitatively explain with Mach waves. So again, the key point is that by fitting the Mach waves to the toroidal flows, these Mach waves produce poloidal flows which are compatible with those recovered from the inversion. And so in principle, we're going to be able to use these to sort of extract properties of the stratified layer. And I would say that the most logical explanation for the strength of the stratification and for the thickness of the stratification that we see is it's in fact due to thermal effects, with heat flux probably about 90% of the adiabatic value. Thanks very much.
Do we have some questions for Bruce?
Take questions. So the question is, since the waves are confined to a layer at the top, is it going to be possible to explain the length of day variations with these flows as has been done in the past? And the answer is that if you think that the flows are only involve the top layer, then the answer is no. But in fact, there are many ways to actually involve the deeper part of the flows to actually get the results that you want. So I would put it this way, that if you think that it's not possible, then you will never find the answer. But I would say that if you believe it's there, right, I'll explain it to you later. I guarantee, let me put it this way. If you invite me back next year, I'll show you how to explain the length of day variations. I think it's possible.
Matthew.
So if the flows, the zonal flows were rigid throughout the core, instead of adding a free wave, you would be forcing this poloidal motion, you would still have the same match
But the toroidal flow, or the toroidal motions, the torsional oscillations, won't excite Mach waves per se, so you won't get the poloidal flows, right? Because they're just going to be zonal flows, and you won't. You have to get to make the Mach waves work. You have to have radial motion. No, I don't think so. I think if you have toroidal motions in the interior, like say torsional oscillations, I don't think that those will couple effectively to Mach waves, would be my claim. I think the solution for the deeper part actually involves the inner core, actually. And I think we can explain the length of day variations. Paul? So, right, so the dominant period in the waves, and I didn't show you the dominant periods, but the dominant period that we pull out from these flow inversions. So what we're constantly doing is we have a model for Mach waves, and we adjust the linear combination of Mach waves that explain the toroidal flows, and the dominant mode that fits the data is a 58-year period mode. And so the 60-year period is no trouble to come up with. So the question is, how do you couple these superficial modes to the deeper flows to get the length of day variations? And that's what we're talking about, and that's what I promised to deliver.
Okay, let's thank Bruce once again.
Thanks.